mechanical engineer by degree. I've also passed the master electrician exam and residential builder exam in the state of Mississippi, as well as a private industry certification program called NABCEP. Our program outline today is pretty robust, so we're going to get started right away. But in this program, we'll be covering everything you need to know to evaluate the preliminary design process of a rooftop solar array. So we'll be covering performance estimation, economic calculations, array layouts, site assessment techniques, shade analysis, um, sizing the inverter to get the relationship right between the array and the output capacity, different interconnection strategies based on service panel amperage. We'll also show how computer-assisted design promotes the generation of project documentation, as well as some final design and permit documentation techniques. We'll talk about racking sizing, which should give you enough skill to complete a specialty balance of system material between the modules, inverters, and racking. We'll discuss aesthetic considerations to keep your array looking good. We'll talk about some advanced installation techniques called internal conduit runs, which I think are particularly important on residential arrays, but have some merit on commercial rooftops as well. After our solar discussion, we will get into battery sizing, both for off-grid and commercial batteries at a very high level. We will detail modeling building electrical demand a little bit further. Finally, we will conclude the program talking about digital electronic load control and how that can complement on-site renewables and battery storage. Let's perform a PV watts example to determine how much energy a solar array will produce. We'll use PV watts to do this, a free and online resource published by the Department of Energy. The same data is by commercial design software for energy modeling, and so PV watts will tell you much environmental data about the project site under a close look, despite its basic appearance. PV watts makes it easy to get a good idea of how an unshaded solar array will produce its electricity for every hour of the day, every day of the year, based on local weather data. Input your address and system size to get started. I recommend performing a PV watts example using a 1 kilowatt solar array size to keep things simple. We can see that a 1 kilowatt solar array in Houston, Texas, facing due south at a 20-degree roof tilt angle will produce 1,400 kilowatt hours of energy per year. Summer days will produce more than winter days because the days are longer. For closely examined input data, the roof tilt information button states that a common 512 roof tilt is at a 22-degree tilt angle. The solar array is facing 180 degrees azimuth, which is another way to say due south. A 90-degree angle would face due east. A 270-degree azimuth faces due west. All this can be modeled in PV watts. Now we know enough to run an experiment. Does a due west facing array perform any differently than a due south array? At a 512 roof pitch, the performance difference between solar arrays is 11%. Similarly, the performance difference between south and east is 11%. If the array is at a steeper tilt, for example at a 1212 roof pitch, which is a 45-degree tilt angle, the performance difference between due south and due east is 20%. Moving north up to Indianapolis, the performance difference between a 45-degree tilt at due south versus due east is 30%. In other words, the orientation of the solar array, or even the tilt angle, does impact array performance, but perhaps not as much as commonly thought. You can find solar arrays bolted 90 degrees down the sides of buildings, such as in New York City, where electricity is expensive and rooftops are cramped.
or for off-grid power in Canada to avoid snowfall. Similarly, at a shallow tilt angle, the north side of the roof isn't off limits. So while east and west facing solar arrays are perfectly fine site selection spots, and even north facing solar arrays in some circumstances are acceptable, most solar in the northern hemisphere faces south. So as far as roof tilt goes, the array will follow the roof. Tilting up off the roof rarely makes sense, especially when the structure is considered. Steep angles will increase solar production, but also increase the installation and operating costs of the system, as the roof will no longer be walkable. If I know for my area, 1 kilowatt of rooftop solar will produce roughly 1,400 kilowatt hours per year, then 1 watt of solar will produce 1.4 kilowatt hours per year. That figure might be discounted 10 to 20% if the tilt angle is atypical, but for the most part, these calculations can be performed mentally in conversation to be later confirmed with a three-dimensional computer model and full shade analysis. But if 1 kilowatt array produces 1,400 kilowatt hours per year, a 5 kilowatt solar array will produce 7